Hello guys, welcome to this tutorial section. In this tutorial section, we look at the design of a microstrip patch antenna. So with the design of the microstrip patch antenna, the calculations are quite involving. So you use EM-Torque for the dimensions of the patch. So over here we need the length and width of the patch antenna. But before you can calculate the length and width of the patch antenna, you need the dielectric constant, the height of the dielectric, and the resonating frequency. So this gives us a length of 39.66 and a width of 47.43. So after you have this, the next step is to use a design formula or a formula from theory. So you use this formula to compute your ZA, that is the impedance at the edge of the patch. After getting your ZA, in our case ZA is 253.80 ohms. So when you have this, you use the second formula to calculate for the impedance to match the edge of the patch. From theory, we are matching a 50 ohm impedance to that of the patch. So we need a quarter wave to link these two sheets to match them, so that we have a maximum power transferred. So the impedance for the quarter wave will be 112.65. So once you have the impedance, that is the second thing you do. You go to EM-Torque, you click on tutorials and tools and select microstrip line calculator. So you enter the impedance, that is 112.65, and electrical length with the parameters of your dielectric and the resonating frequency. And this gives us a width of 1.08 and a length of 22.75. So once you are done over here, it is left with the dimensions of your 50 ohm feed line. For that, it is very easy. You need to key in your 50 ohms and the other parameters, and you have 4.92 as your width and a length of 21.93 as the length of the feed line. So once you have these values, we can go ahead and design the antenna. So you first on the rectangle. Once it's done loading, we can rename it. Rename it as patch. And we change the dimensions. With patch antenna, you have to change the width and length to get your desired frequency. So it is very good to design with variables instead of keying the actual values. So over here, I'll represent the width by capital W, which is 39.66. And the length with capital L, which is 47.43. After that, I want to align it at the origin, where half of the length will be at the left side of the principal axis and right side of the principal axis as well. So I think I've already explained it. There is no need to waste time on it. So the height of the substrate is small t. So you have to enter 1.6 and you set it to length. So this is what we have. We do fit all, and we can change the color. I prefer to use this color. Okay, we are done with the patch. And what we need is this is what I was talking about. So we will design it in such a way that half of the length is below the red line and half of the length is what above the red line. That is why we need to divide the position into two. It's time for us to draw what the quarter wave line, and I'll rename it as what kill wave. Change the color, and over here we want it to start from the tip of what the edge of what the patch. So we will start from half of what the width. So this covers what half of the width in the positive what S direction. So we will click on create rectangle. The starting point will not be negative now, it is half of what the width. Now you have length of what quarter wave, which is 22.75 mm. You have width of quarter wave, that is 1.08 mm. This is what we have just at the edge of it. So now we are left with what the 50 ohm feed line. So I'll change the color, I'll change the name to feed line. The dimensions over here too, we started at what half the width plus the entire length of what the quarter wave. So we will do half width plus length of quarter wave. The length of the feed line is 21.93. Width of the feed line is 4.93. So that is it. Sorry, I didn't change these ones. Good. Everything is on point now. We can rotate it. What we need is what our substrate now. So I'll change the color, change the name to what substrate. I'll change the material. We are using what RT diode of dielectric constant 2.0. so this is it. Let me confirm. Okay, 2.2 rather, sorry, 2.2. I will change. So now I want it to start from what the tip of what 50 ohm feed line, and that will be what half of the width plus the entire length of what the feed line and what the quarter wave. So we have half plus LQ plus LF. Now the actual length, since we started from the positive, we need to move to the negative. Do you get it? So we have minus 115, and over here too it will be 105, and you will start from 0 and end at what? T, that is the height. Here we will divide it into 2, that is 105 divided by what? 2. Everything is okay now. So we are left with what? The ground. Let me copy this because the ground will start from the same place. So we have Control C, ground. Change the name to what? Ground. Okay, I'll change the color of ground. Okay. Now start ground from the same place. To minus 115, 105, 105 divided by 2. So that is the ground. After this, you have to assign what? Our port. And you assign our port. Now I need to change the plane first because I'm no longer working in XYZ, I'm working in what? YZ. So I'll pick it up again. Change the name to what? Port. Let me change the color to red. So I need to change the dimensions of what? Port, because it has exceeded what? The edge or the tip of the feed line. So I'll have minus T over here, while I have 4.93. We'll start from what? The tip as well. So Control V. That is it. So now we can now assign our what? Excitation. Define the line. It is defined with no error, so we can finish. Fit all. Now we need to assign boundaries to what? Our material. So I will select on patch, click on patch, add the quarter wave, and add the feed line. That's how they look like. And I will assign what? A boundary to them. The boundary should be what? Perfect E. So I've assigned my first boundary. Let us confirm. That is it. And let us confirm our excitation to. Excitation to is on point. So now ground is unassigned. We will assign ground to perfect A, and we are done with the citations. The next thing that we need to do is to change the plane and put a boundary around what our antenna. So we call our boundary what radiation box. It's like a space, the region where the antenna will work. So rad, and it should be very big enough to contain what the entire antenna. 230. So minus 200 divided by 2 gives us minus 100. We have minus 100 as well, and what's minus 30 divided by 2 gives us minus 15. So I've covered the entire antenna. What we need to do is that we should change the transparency so that we can see how the antenna is what aligned inside. Good. So now we need to assign radiation to what? The boundary. And we are done. The next thing that we need to do is what? Solution setup. Go to advanced. Our center frequency is 2.5. Number of passes are limited to 15. Can do okay now. Now, since we have a center frequency of what 2.5, we need to determine what our start frequency and what ending frequency. But we know that from theory, f1 plus f2 divided by 2 should be equal to what our center frequency. So if you start with 1 gigahertz, you need to solve for what f2. If you start with 1 gigahertz, we know that our ending frequency will be what 4, because 1 plus 4 will give us 5 divided by 2 gives us what 2.5. Hope that part is clear. I will change to 400. I don't like 401 from interpolating to what fast. Okay. So now we go to validation. Everything we have is what on point, so we can simulate now. So we analyze all. Before we analyze, we will rename our project. So patch antenna underscore dot. Alright, so the simulation is done, so we can go ahead and look at our results. It says normal completion of simulation on server. So we go to results and plot what? IS11. Okay, so this is IS11 and it's looking great, just that it is not on the resonating frequency. So I will show you at the end of this lecture video how you can make it lie on what the resonating frequency, but we need to check our bandwidth. Okay, so we will use a marker. So with the marker we want Y marker, so we will change this to 10. Okay, we have 10. So now you add a note. This is how you should present your work doing what the exam. So you write bandwidth of device. So bandwidth of device. So the bandwidth will be 2.44 minus 2.41. And you put it there. So over here you see that the bandwidth will be what 0.03 what gigahertz. So this is how it should be. you can convert to megahertz as well. So that is it. This is how you should present your work during the exam. Once we are done with this, we can set up our infinite sphere and check the other parameters of the antenna. So this is for the 2D. We start from 0 to 360. And that's 1. Step size of 1 minus 180 to 180 with a step size of 5. You have that one. You set another one for the 3D polar plot. Minus 180 to 180, we end at 2. And you have 0 to 180 with a step size of 5. Sorry. So you go ahead and plot our far field results. You first of all plot forward the 3D polar plot. Make sure 3D is selected over here. Gain total, unit dB, and we will look at our new results. Good. This is our 3D polar plot, and over here we have an idea of the gain of the antenna. So the maximum gain is 7.5. It shows you that it is a directional antenna. The signals propagate from this side, and it is directed towards the right side, where we have a maximum radiation. So that part is indicated in red. And when you look at the legend, red is between 6 to 7, and our maximum gain is 7.1. It is good for a directional antenna. So we go ahead and plot other far field results. You look at the radiation pattern. We look at the H plane. You select gain phi and gain theta. You select dB. Go to families. We won't plot all for phi. So we first of all look at the H plane. That is for phi at 0. You generate the report. Good. So over here, this is what we have. We will add a marker to check the front to back ratio. Okay. You add a note. This is how you should present your work. So front to back ratio. Front to back ratio. So you check the magnitudes and you subtract them. So the front to back ratio would be 23 dB. So 23 point something. So usually you need to ignore. So this is it. Those of you who wouldn't get it, 7 minus 16, and you have front to back ratio of 23 dB. Good. You add a note. After that, you need to add another one and compute the half power beam rate. So we will add other markers. We move to this direction, and when you are moving towards that direction, we should check what's the M1, the magnitude. So it should be 3 dB less of the magnitude. So when we have 4, then we stop. We have 6. You should be checking this side. We have 6 point something. So 5. We have 4. So we can leave the marker here, and we start from this point. It should also be 3 3 less than the magnitude that we have. Okay. So with the half power beamwidth, we are looking at 3 dB less this value. Okay, so we will be moving. That value was 7 point something, and we had 4 point something for this one. So we have 5. So we have 5 over here. Okay, 4.6. So we can place our marker here. Thought we had inserted. Okay, so this is it. We have 5 point something over here. We have 4.4. So 4.4 is fine. So you will subtract. You don't have to subtract. So just insert and dot. You say half power beamwidth should be equal to 35 degrees minus 25. So we have 60, right? So that will be 60 degrees. Good. You do okay. You are done here. There is a mark for all of these stuffs, and for the cross polar showing them inside, that is the red diagram inside the H-plane. There is also a mark for it, so try your best to do all of these. And the next result is the E-plane. So you go to far field report, radiation pattern, 2D selected, gain theta, gain phi, dB, go to families. We plot for 90 degrees now. So new report. Good. Over here too, you measure what? The front to back ratio, and after that we look at it's 7, so we go to 4 point something, remove the cursor until we have 4. So 4.6 is over here, move to this side until we have 4. 4.7 is over there. Good. So now you add note. Now the front to back ratio. Ratio is what? 7 minus 16. So you have 23 dB. You add another note. Half power beamwidth. And that one is also equal to 35 degrees minus 35. So for that we have what? 70 degrees. So we are done with the design of microstrip patch antenna. But over here, our results, we want this to lie on the tip of what? The 2.5 gigahertz. So what we do is that based on the formula, which is C lambda equals C divided by F. So we want a very huge frequency, because the frequency which we have right now is around 2.4 something. We want to go higher. So if we want to go higher, the size of the antenna is inversely proportional to what? The frequency, which means that if you want a higher frequency, that is 2.5, we should reduce the size of what? The antenna, or a part of the antenna. So over here, what we do is that we'll go to our design properties, and with the length, we reduce the width by 1.3. These are values that I tried. It doesn't mean that it will work for you. You have to be reducing them with reasonable unit. Let's say a unit. So first time you use 1, you add a decimal, you use 2 until your result is better, and we reduce just 1 from the length. So we can now do OK and run the simulation again. Alright, so the simulation was done. We had these errors because the dimensions were adjusted. So this is the results. As you can see, it is on 2.5. You can look at the gain. I think things won't change that much. Okay, 6.8. Everything is on point. So guys, all the best with your exam, and you meet again. Bye.